Okay, so when we have non-periodic functions, then Fourier series cannot be used to approximate those functions. Because it will not give you a very nice approximation. Then we go for Fourier integrals. So and from these integrals only we will learn about Fourier transforms. So what is Fourier integral? So before that, for non-periodic functions, our period will be infinite, right? Because they are not never going to repeat. So period will be infinite. It means the value of L. So that was period was equal to 2L in our Fourier series. So value of L also is going to be infinity, right? So firstly, I'm writing Fourier series here. So it was f of x is equal to a0 plus sigma n is equal to 1 to infinity an cosine of n pi x by l plus bn sine of n pi x by l, right? Where n was a positive integer. Now, so this function is a periodic function with period L. So I'm denoting, I'm just changing the notations. So I'm denoting this function, periodic function with FL. FL means a periodic function with period 2L. Okay. And this can be written as n. One more thing I'm doing. So let me just, so FL right? This is our FLX. And then we have I'm replacing Wn, okay, right? So finally, what we will be able to write as FLX is equal to A0 plus sigma n is equal to 1 to infinity an cosine of Wnx plus Pn sine of Wnx, right? Where Wn is n pi by l. Now this A0, these were the coefficients of Fourier series. So if you remember, A0 was 1 by 2L minus L to L FL of x dx, right? And then we have an is equal to 1 by L minus L to L FL of x. Suppose here I'm writing n pi x by L, but you can also write Wn into x. And then we have Pn, which is 1 by L, and that was minus L to L FLX sine n pi x square, right? It was there. Now, if I denote this x with any another variable, let's say I call it v, it is not going to matter because it is a constant value. So if I write it FLV dv, FLW dw, FLP dp, it is not going to matter because after integration it is going to give you a constant value, right? So what I'm going to do right now, I'm interchanging here in this coefficients. I'm interchanging x with v, okay, and obviously dx with dv. So if I do that, so finally my FL will look like, so and I'm also substituting these coefficients in the series, in the Fourier series FL. So if I do that, so expression of AW is 1 by 2L and minus L to L FL VdV, right? I'm just writing VdV here, plus. And if I substitute AN and BN in this equation, so 1 by L will be common and I'll just write it here, 1 by L. So I'm writing here 1 by L and sigma n is equal to 1 to infinity. And then I have this cos omega nx, which I'm writing here. And then the value of an, which is minus L to L FLB cos omega nb dv, right? So that's what I'm going to write, minus L to L FLB. I'm calling it as omega n or wn. So please understand this wn only. You can write it as omega also. So it's the same thing. So I will use w and omega interchangeably in my lecture. But you please understand that either it can be w or it can be omega. So this was wn v dv will be there, right? Plus we have minus L to L FLV sine omega n v and then v, right? This completes our function. Now, few more things I'm going to do here. So, what is my omega n? My omega n is n pi by L, right? So my omega n plus 1 will be n plus 1 pi by L. And then my delta omega, that is change in omega, which is omega n plus 1 minus omega n, right? And these n were nothing but the terms of the Fourier series, right? So if n is 1, so it is the second term of the A is 0, A1 and B1 combined together makes the first term, then A2, B2, and so on. So it's kind of difference between uh, two omega, the two W's of the two terms of Fourier series. So this can be written as n plus 1 pi by L minus n pi by L. So you will be left with pi by L. So here what we can do, what we can conclude from here is that 1 by L is equal to delta omega by pi, right? Delta W by pi or delta omega by pi. So let's just substitute here. So if you do that, what we will get? And also, okay, so let me do that first. So here I'm not doing it, so it will be first term is as it is. So this first term is as it is. And the second term, 1 by L I'm going to substitute as delta omega by pi. So here 1 by L I'll put as delta omega delta W by pi. So 1 by pi I'm keeping only, and I'm shifting delta W here at this point and at this point. Okay. So I think I missed a term here. Yes. Here actually sine omega and x will come. Right. So what I'm doing is so pi delta by pi. So L is delta omega by pi. So L is equal to 1 to infinity and cosine omega and W and x. And I'm putting one delta omega here or delta W here, and then minus L to L FLV cosine so dV, and then there was a big bracket here and plus, and I'm putting one omega and here at this point delta omega. Sorry, I'm putting delta omega here and minus L to L FLV sine omega and V. Right. Now what I want to do is there is something okay. So for non-periodic functions, L goes to infinity. So if L goes to infinity, right? So then what will happen to delta omega? Let's see. Delta W. So delta W will go to, because delta W is 1 by L. I mean proportional to 1 by L. So if L will go to infinity, delta W will approach to 0, right? It means our delta W will become dW, right? Means this will become dW, because when delta W is very small, then we can write it as dW. Anyway, so now if you look at this series here, so this term is the function. So let me just highlight. So this term is a function of omega n. This whole series, this whole thing, if we will solve, so this will be a function of omega n, right? This whole integral. And this sine omega n is also a function of omega n. Again, will be a function of omega n. Because if you are solving in terms of v, so v will disappear and it will come in terms of L, but finally omega n will be there. So if there is, let me just tell you what I'm going to do. And firstly, here I'm using omega n on the x-axis. And let's say there is some function p of omega n on the y-axis, right? And we were going like this. Okay. And omega n, if you see here, omega n is n pi by L. And when n will be equal to 1 and L will be infinity, it will be approximately 0. So I'm starting from 0. So, and we have, let's say, p of omega n, something like this. I don't know, maybe like this. So as of now, what we were doing, let's change this with omega only, not omega infinity. W. So what we were doing is, firstly we were taking, let's say here, firstly we are taking n is equal to 1. Let's say this will give some omega initially. So let's say I'm calling this as omega 1, right? And then delta omega will be this thing, right? Because at n is equal to 1, you have omega 2 minus omega 1. So we here we have, let's say, omega 2. So this is delta omega. And if I multiply, okay. And what we are doing here, so firstly we are taking So this is also a function of omega n, and this is also a function of omega n. So I'm considering that this whole thing is a function of omega n. I'm calling it as p of omega. So p of omega n multiplied by delta omega. So what? So p of omega n means p of omega 1, which is this height, right? And multiplied by delta omega, which will give me this rectangle, area of this rectangle, right? And then you will go for the next one, and you include this function also in this case, because delta w you can take common, and then you have p of w and delta w multiplied together. So p of w will come from this function, this function, this function, and then this function. So and then you keep on doing that, so you will get omega 3. Again, this is delta omega, and then you are again taking this height, and you keep on doing it. You are trying to do in this series, in this summation up to infinity, you're trying to approximate the area under this curve. And what is this function? So this function is nothing but cos of omega x, an integral of minus L to L F L V cos of omega x omega v dv, and then plus sine of omega x and minus L to L F L V sine of omega v dv. This is p function. We are trying to omega infinity, okay, through this sum. Now, what will happen when our delta omega will be very small, when L will approach to infinity? So when L will approach to infinity, our delta omega will become d omega, and then this approximated areas will be equal to exact area in this curve under the curve, and we can represent exact areas through integrals. So then we can directly write that this area is integral of p of omega d omega, or p of w dw, right? So now omega n will not be discrete, it will be a continuous function, because the our L is very, right, and even if you take n is equal to 1, 2, 3, 4, our n L is this much from here to here, and it is very large. So if you do n is equal to 1, 2, 3, 4, you're going to you're going to take an increment, very small increment, right? Because our L is very large. So n pi by L, if you increase n1, n is equal to 1, 2, 3, 4, 5, 6, 7, 8, and so on, you're going to take very small increments. So then we say that L as approaches to infinity, omega becomes continuous variable, it's not a discrete variable. So what I'm trying to say is, as L will approach to infinity, omega will be d omega, and then this summation here will convert into integral. And the first value will be 0, because if n is equal to 1, L is infinity, the first value will become 0. Anyway, so let's do it. And this quantity here. So this quantity here is because FL is a periodic function, right? And you are integrating it from minus to L. So any periodic function, if you integrate, so is infinity. Any periodic function, if you integrate from minus infinity to infinity, you're going to get some finite value, right? And some finite value will be 0. So this term is going to be 0. Yes, someone wants to ask any question? So this term is 0 plus, we can say that we have 1 by pi here, and then we are going from 0 to infinity, and here we have d omega outside. I'm taking or dw outside, and then I have cos wx, and then this integral of minus infinity to infinity, this integral here, minus L to L, so L is infinity, minus infinity to infinity, FLV cos wv dv, right? And okay, plus we have the sine term also, so we have this sine omega x minus infinity to infinity FLV sine omega v dv, right? And then d omega. So you see that our integral has converted, our series summation has converted into integral. I'm sorry, my internet had stopped. Are you able to hear me? Earlier, my mic was not muted, right? Was on. Can someone confirm whether it was muted or it was on? Okay. So yeah, so we were here. So what I wanted to tell you people that now we have converted our, so this is known as integration as a limit of sum. So we can convert our integration in our summation into integration whenever this delta omega is very small. Okay, so finally, this is what I'm getting as FLX. And one more thing, it is no more FLX, it is non-periodic function. So I'm denoting it as FX. So here I want to make it clear that my fx again is a non-periodic function now, and it is limit L approaches to infinity FLX, right? That's what we have done. We have, so in this function we have put the limit L approaches to infinity, and then this becomes a non-periodic function. So our f of x is this 1 by pi, this whole thing. So now, and this is also now a non-periodic function, and you can read about this integration as a limit of sum here that I've written, or it is also known as limit Riemann sums. So approximating area under a curve using finite rectangles or trapeziums or something like that is, it is, so this is known as Riemann sum, and when this change is very small, then it is known as limit of the Riemann sum, and that is equal to integration. Okay, that's why we call integration is a summation. Anyway, so now we have, finally we have this f of x. I'm just writing again in some easy form. So f of x we can write it as a of omega cos omega x, right? Plus b of omega, b is a function of omega, sin omega x, and then we have d omega, where our a omega is nothing but, if you see from here, from this expression, which is minus infinity to infinity, fl fl of b, it is a periodic function. So now, yeah, so here also FL will not come, F will come because it is no more periodic function. So this is F of V. F of V cosine of omega V dV, right? And then we have B of omega, which is minus infinity to infinity, F of V sine of omega V dV. Okay, so now what I want to say here, so these two coefficients are also some kind of transforms. Why they are transforms? Because if you notice carefully, here you can interchange v with x, right? Because it's not going to matter f of, if you integrate, because it's not going to matter whether you put p, v, whichever variable you take. So you can take x also. So it can be f of x cos omega x dx. And the answer is coming out to be, answer will come in terms of omega, because you will put the limits of x minus infinity and infinity, and it will get cancelled out. Anyways, I mean, it will be in terms of some finite number. What I want to say here is, You are transforming f of v. So this f is in terms of v, and now you are changing it in some another variable omega. So this is also a transformation where you are transforming function in terms of v, where you are transforming your function which is in terms of v to a new function which is in terms of omega. Here also you are doing it. So here you are transforming your function f of v into a new function which is in terms of omega. So later on we will see that it is known as cosine Fourier transform and this is known as sine Fourier transform. So it is the building block of Fourier transform. And these are used in solving ordinary differential equations and partial differential equations. And you will see that this will be algebraic function of omega. So we will convert whatever function we take, we will transform into a space where the functions becomes algebraic. And it is very easy to deal with algebraic functions, right? Polynomial functions or algebraic functions, it's very easy to deal with them. So if you are able to convert your differential equation into algebraic equation, then it will be very easy to solve it. Similarly, if you are able to convert any function into algebraic function, you are taking a function into some space where it is expressed in terms of any other another variable, so it is known as algebraic function. Sorry, transformation. Anyway. So this is known as a Fourier integral, all three combined together. And it is valid for non-periodic functions as well. I would like to take one example where we can apply this Fourier integral for non-periodic function. So let me just take it. For example, find the Fourier integral of the function. So our function is like this: f of x is equal to 1 if modulus of x is less than 1, and it is 0 if modulus of x is greater than 1. It is a non-periodic function because if you will plot it, f of x. So this is your 1, and when your mod x is minus 1 to 1, then your x is minus 1 to 1, then this function is 1. Otherwise, it is 0. So this will look like this function here, right? So it's a non-periodic function. It's just like one pulse. Now let's try to find out this Fourier integral for this function. So firstly, we'll find these coefficients. I'm calling it as coefficients of this integration. Anyway, so AW, which is nothing but minus infinity to infinity. Okay, I think I have forgotten one more thing. So it is 1 over pi also here because 1 over pi was here, so we should not forget about it. 1 over pi will come in AW and BW. Okay, so you can just calculate AW, which is 1 over pi and minus infinity to infinity. FV was omega v dv, right? So, but this function is 0 everywhere apart from minus 1 to 1. So this integral will be left with. So this integral will go from minus 1 to 1. Other than that, minus infinity to minus 1 it is 0, and infinity to and 1 to infinity it is 0 because f is 0. So then this integral will be minus 1 to 1 here, and fb from minus 1 to 1 is 1, and then here we have cos omega v dv, right? So finally, if you integrate this, so what you will get? So here you will get sine omega v divided by omega, and then you have minus 1 to 1. So then if you put 1 here, so you'll get finally 2 sine omega, 2 sine omega. by omega, sin omega by pi omega, right? So this is your AW, and now let's calculate BW, B omega, which is 1 by pi minus infinity. So I'm just writing minus 1 to 1 because all the other in all the other intervals it will be 0, and your f of v is 1. So finally you have sin omega v and fd. So integration of sin omega v is nothing but um, minus of cosine of omega v divided by omega, and then pi will be there, and then you minus 1 to 1. So if you do that, so cos of omega v, so cos is a or even function, so cos of minus 1 will also be 1, so it will be 0. This will give you 0, so d of omega is 0. But finally your function is what? F of x is nothing but if you see here, it was 0 to infinity a omega cos omega x. So a omega is nothing but your 2 sine omega by pi omega, and then cos omega x 0 to infinity, and this is t. And then here you have d omega, right? Yeah. So this you have to keep in mind that here you have d omega, here you don't have d of x. If here you would have d of x, then this whole thing will be a constant, not will be a function of x. Anyway, so finally you have this. So I would just like to write it in some. So I'm taking this constant out. So you have 0 to infinity sine omega and divided by omega and cos omega x, right? And d omega of x. So what here we want to prove that this thing is going to approximate this function here, non-periodic function. And if you remember in Fourier series, we did partial sums. And in while doing partial sums, we take first only the first term, then first two terms, then first three terms. Here, for taking such kind of thing, here we have to limit this. We have to constrain this upper limit. So let's say we want to evaluate some partial integral. So we will go from 0 to a and then 2 by pi. And we will see what will happen with different when we will increase the value of a, right? Cos omega x d omega. And I'm going to share my laptop screen now. So, but maybe I have, okay, maybe I have Desmos here also. Let's do this here. So our function was, so I'm denoting it with y. So y equal to 2 divided by pi. Here pi is gone. And multiplied with, then I have integration. Integration was going from 0 to, let's say, some number a, okay. And then here you have, then we had sine omega, or let's say w, I'm taking w bracket close, and then we have cosine omega x, cosine omega x, and then bracket close, and I have d omega, so dw, right? And of course a is our, and a is our variable here. I mean, we will vary a, so I've taken a as a slider. And then one more thing, here we have division by omega as well, so this division by w. Okay, so now let's see what happens when we, so this is our function. You are able to see when a is 1, so 0 to 1. Now let's increase our a, and if you see here, this is our 1 here, 1. So our function was a step function, minus 1 to 1 it was 1, and then it was 0. So let's increase a. So if you see what is happening, now increase a more. You see what is happening, now increase 8. So our this integral is trying to approximate our original function, which was in between -1 to 1 it was 1, and other anywhere else it was 0. So now this function is trying to approximate that function. And when a will approach to infinity, now it will be exactly that function itself. Let me increase a more. So let me just see if it is possible. Let's take a as 100, starting from 1, step of 1. Okay. And then increase a more. Let's see what is happening now. A is 30. Let's see if we put a as 70. I think it will not evaluate because, yes, no, it is evaluating. So see, it is approximately equal to our function, although there are some variations because it is a approximation only. But when a will go to infinity now, so let me just do it for 100. Let's change. I don't think so. Let's take 8,000. I've not tried it, so let me just. Oh, it's going up to 10 only. Maybe it will not go to 1,000. Anyways, this calculator may have some limitations. So I think it is not calculating for 1,000. This calculator may have some limitations in terms of at the back end it might be doing numerical integration. Anyway, so but you would have got the idea that we are able to approximate a non-periodic function as well with the help of Fourier series. Fourier integral, not the Fourier series. Okay. Uh, so let's go to the next part. Okay. Now, now we are going to study about Fourier transforms. This was all about Fourier integral, and obviously you can find out for Fourier integral for any kind of function. Okay. So then in your exam you may have questions like you will be given a function and you will be asked to find out Fourier integral of that function. So first you have to find a omega and b omega, and then you have to put a omega and b omega into this integral, and you have to do, and you can leave it in this integral form itself, right? So because this integral form will approximate x, or you can solve for omega. If you are able to solve for omega, it is fine. Then whole function will be in terms of x only. There will not be integration. But if you are not able to solve for omega, then also it's fine. Now let's do Fourier integral, Fourier transform. And there are a lot of things in between, but I'm skipping it for the time being because maybe it's not in your syllabus. So let's quickly get to Fourier transform. So as I told you that in between there is this. Uh, so this is known as a so in between you have this also in where you use this expression to transform from x to omega. So you have function in terms of variable x, and then you transform that function in terms of you transform that function into a new function which is a function of omega. So this is known as Fourier cosine transform, and this is known as Fourier sine transform. So in between this is also there, but I'm skipping it for the time being. You can read it from Kreyszig, and I'm just going directly to the Fourier transform. So Fourier transform is not only for real numbers, it is a complex, it is also valid for complex numbers. So it is a complex transform. These two are real transforms that I'm telling you. This Fourier cosine and Fourier sine, these are valid for real functions. But Fourier transform is complex transform. So we can say that this is a complex transform, or it deals with complex numbers. So firstly, shall I write the definition of transform? So transform is something which transforms your original function into a new function, which is a function of new variable. Okay, and then that new function is maybe easier to solve because that is an algebraic function. You would have done same thing in Laplace transforms as well if you would have studied. If you have studied it, so in Laplace transform also we transform our original function into new function which is a function of another variable. Anyway, so let me just firstly we will define what is complex Fourier integral. So we know that what is Fourier integral, but now we are going to define complex Fourier integral. So Fourier integral is the limit of Fourier series for non-periodic functions. So now it was 0 to infinity a omega. It was 0 to infinity. Yeah, so it was 0 to infinity a omega cosine omega x plus b omega sine, sorry, sine omega x and then d omega, right? And then a omega was defined like this: 1 by pi minus infinity to infinity f of v cosine of omega v dv, and then b of omega, which is 1 by pi minus infinity to infinity f of v sine of omega v dv. Anyway, so now what we are going to do is you have to put a omega and b omega in f of x. That we have done before also, but I mean in the original series we had a omega and b omega in f of x only, but we are going to do it now as well. If you put that, so what you will get? So f of x will be 1 by pi 0 to infinity and then minus infinity to infinity, because this integral will also come now when I will put it here. So and finally this f of v is it is in this a omega and b omega, so this will come as common quantity, so we can write it like this: f of v, and finally you have cosine omega v and then cosine omega x plus sine omega v sine omega x, and then you are integrating first with respect to dv and then with respect to dw d omega, right? And so I've just substituted these expressions into this function, so you will get finally this expression. Now I'm going to use this formula: cos a cos b plus sine a sine b is equal to cos a minus b, and you can write it as cos b minus a as well, because cos is a even function, so cos of minus x is cosine of x only, so you can write it like this also. So finally I'm going to apply this formula and I'm going to use cos of b minus a. If you apply it here, so finally what you are going to get is your f of x is 1 over pi 0 to infinity and then minus infinity to infinity f of b, and then you have cosine of omega x minus omega v, right? and then dv, and then this whole quantity we will integrate with respect to d omega or dw. Okay. Now you see here, there are few observations that we have to make. So let's talk about this integral. Whole integral, okay. So I'm talking about this whole integral. So this is, so when you will integrate, it will be in terms of omega, right? Because v, whatever v will be, you will put these limits against v. So it will be in terms of omega. But this function is even in terms of omega, right? Because if you replace omega with minus omega, nothing is going to change for this integral because cosine is anyway even function and omega is not appearing in f, right? And so this whole integral is a even integral. So even integral are those integrals, if you remember. So if this is x-axis and this is the even function f of x, so it looks symmetric about y-axis, right? So because for minus x also value will be same and for plus x also value will be same for s for same magnitude of x. So what we can say is if you are integrating from 0 to infinity, you are getting some area or some value of integral. And if I integrate from minus infinity to infinity, I will get double of that value, right? So then I can write this integral as, if I do it from minus infinity to infinity, and if I do it half, then it will be same as that of the above integral. Because minus infinity to infinity will be double of the above integral, and I am also already doing it half. So finally you will get this one. So you get 1 over 2 pi minus infinity to infinity above as well, and then here also f of v cosine of. So we can, I'm just saying that here it is even function. Well, yeah. Okay, so we have got this. And if I write like this, let's say, so this is f of x. I'm just writing another function, which is, let's say this one. Sine of omega x minus omega v. So can someone tell me that what will be the value of this integral? This integral that I have written here. Yes, someone please. So it is a sine is a even function or odd function? Yes, tell me. Yes, it is odd function. So for odd functions, if you draw the graph, it will look something like this. So let's say if you have there omega and here you have some function f of omega. So your odd functions will look like this because your f of omega and f of minus omega are exactly opposite in sign to each other. I mean, the magnitude is same, the signs will be opposite. So what I want to say is if you integrate from minus infinity to 0 and 0 to infinity, it will give you 0 because the area below the x-axis will be equal to area above the x-axis, and this function is again sine of omega. So it is odd function in omega. So finally, if you will integrate in terms of omega minus infinity to infinity, so this will give you 0 because this is an odd function. This integral here is odd function of omega. Okay, so now um, okay, now I want to write it in some another term. So let me just do it this way. Can I, if I add this quantity to this integral, nothing is going to change because this is anyway zero, right? So let me just add it. So now my f of x can be, and I'm going to multiply this with iota, which is imaginary number, but again it is zero, so iota multiplied by zero will also be zero. So what I'm going to do is I'm just going to do this. Let's just see. So I'm just doing f of v cos of omega x minus omega v plus iota times f of v sine of omega x minus omega v, right? And then I have here uh, dv, and then you can say that this whole integral. Here I have dw, right? So this quantity here inside, I just added these two terms because this is zero anyway. I mean, this is not going to make any difference. So can I, so this quantity can be written as, if you remember, e raised to power I alpha was what? So cos alpha plus iota sin alpha, right? If I take fb as common, so this is nothing but cos omega x minus omega v plus iota sin omega x minus omega v. So this is nothing but e raised to power I omega x minus v, right? So this will be cos omega x minus v plus sin omega x minus v, right? And iota will also there. So finally, your f of x will be 1 by 2 pi minus infinity to infinity. And then again one more minus infinity to infinity, and f of v will be common, and then f of v will be common, and then we have e raised to power iota omega x minus v, and then we have dv and d omega, or dw, you can say. So this is known as Fourier integral, Fourier transform. I'll tell you why it is Fourier transform. So this is a transform because you have here and okay, you have here some function, right? Initially, let's say f of x is given to you, so you can write it as f of v also. So you have here some function, right? And just let me see. I think I made a mistake. Will this be f of x or f of v? Yeah, so this will be f of x, the non-periodic function which we were trying to approximate. And sorry, this is not a Fourier. Yeah, just let me check one thing. So here we have, okay, so x is here, and it's fine, it's fine. So yeah, so this is, so omega is here, so you will integrate with respect to omega also, v also, and there is no integration with respect to x. So x will be left, so left as it is, and that's why this whole thing will be a function of x. This is known as complex Fourier integral, not the Fourier transform. So this is complex Fourier integral. And Fourier transform will originate from, because if you remember, we had a Fourier integral first, and then we said that the two coefficients that were coming were um, sine and cosine Fourier transforms. Here, similarly, here also we have complex Fourier integral, and from here we will get Fourier transform from the coefficients of this integral. So let's see how. So So for Fourier transform, I am doing some readjustments. So I can write f of x is equal to 1 by root 2 pi minus infinity to infinity. And again, I'm multiplying with 1 minus root 2 pi. So this will be multiplied together will be 2 pi only. And then I'm taking this minus infinity to infinity here. And I'm just writing f of v. And then I'm writing e raised power iota omega v. This minus 1 to the inside. So minus iota omega v here inside and dv, right? So I'm writing it here, and then outside I have this iota omega x and d omega, right? So here also I had the same thing, if you remember. I just want to correlate. So here I have a omega, b omega, which was an integral of v, right? And from integral of v only, we said that these are transforms because it transforms function in variable v into another function of variable omega. Similarly, and omega is something, if you see here, it's kind of coming into cosine. So it is kind of frequency only. So you see here that some function in some another variable, we are just transforming into frequency domain. We can also say like this. Okay. But here also we will do the same. Mm. So there our coefficients which were involving integral with respect to v were used in were named as sine and cosine Fourier transform. Here also our integral which is involved in integration of v with respect to v, this will be named as Fourier transform. So I'm just writing this function here. So this is Fourier transform, and this will be a function of, let's see, 1 by root 2 pi minus infinity to infinity f of v e raised power minus iota omega v dv, right? And this will be a function of omega because your v will be integrated and limits will be there. So v will disappear and then omega will be left. So again, since you have iota omega here, so this will be, so imaginary part we have taken to this side, and here also there is imaginary part to the whole this whole function also has some this imaginary part, but combined together it can be real also because this we said that this integral will be zero. So combined together, we started with some real function, but now we are utilizing into imaginary parts also individually. Anyway, so this integral here is known as Fourier transform, which is coming from complex Fourier integral, and it transformed a function in variable v into a new function of variable omega. And it is entirely a new function. It is not necessarily the same function f. So let me just name it as some different thing. Okay, let's name it as f omega as of now. And it is also, it can also be called as capital F, which is Fourier transform Fourier transform operator, applied on this function f of v, right? So if you apply your Fourier transform operator on some function, then your function will be some new function in some new, in this new variable omega. And omega, if you also see, if you expand iota omega v, so it will be cos omega v plus iota sine omega v. So omega is again coming in the angle of cosine and sine. So angle can be related to frequency if we are dealing with time. So basically, in structural dynamics or vibration of structures, we use Fourier transforms to transform the function from time domain to frequency domain. So, and sometimes it is easier to deal in frequency domain compared to time domain. And we do reverse as well. Anyway, so this is known as Fourier transform. Okay. Um, and you know that I can replace this v with x also, because it is not going to matter whether I take v, p, q, r, anything else. So what I'm going to now do is, because usually our function, original function are given in terms of x. So if I apply Fourier operator or Fourier transform on some function x, then I will get new function in terms of omega, and that is given by f of x e raised to the power minus iota omega x dx. Okay, so finally I have this one. So this is known as Fourier transformation. And then we have inverse Fourier transformation also. So what you can do is you can put your f of omega here in this complex Fourier integral. So I mean, this was the complex Fourier integral. So if you put f of omega here, so what you will get f of x. So let me do that. So finally your f of x will be 1 by root 2 pi minus infinity to infinity, and you put f of omega here. So you will get f of omega e raised to the power iota omega x, and then d omega, right? Yeah. So here what you are doing is you have some new function f of omega, and you are transforming your function from omega space to the x space, right? So you are inverting it back. So this is known as inverse Fourier transform. And it looks exactly same. There is no change, only we have change of variables. But you remember this function is different compared to your original function. It is not f of x, it is f of omega. So don't do a mistake that at the place of x you just put. Let me just put a subscript here, then it will be clear. So it is f subscript omega. So it's a different function. So it is not same as the function f. Okay. So if your original function is this, you can transform into a new function which is a function of omega, and then if you have this already the function in this omega space, you can get your original function f of x using inverse Fourier transform. I think this completes your Fourier analysis chapter. So sometimes we also write it as f omega is a function which is a function of omega. So apply Fourier operation on this f of x, so you will get this f omega. So this is known as Fourier transform. And then if you're if you want to get f of x from f omega, then you have to apply inverse Fourier operator on your function f omega. But this is also one of the notations. So inverse Fourier transform. And you can practice many questions from Kreyszig, but I would like to cover a few more things. We will take a break of 5 minutes, then we will resume. Then I will teach for another 15 minutes. Okay. We'll take a break of 5 minutes. Are you people back? Can we start? Okay. So then I would like to talk about existence of Fourier transforms. That when will these Fourier transforms exist for what kind of functions? So we say that if f of x is integrable on the x-axis and piecewise continuous, means if it even if it is a step function, then also it is integrable, so it means it can be piecewise continuous and piecewise continuous on every finite interval. Then the Fourier transform f w omega exists. So if f of x is integrable, means it should not go to infinity. Its integration should be finite. So if f of x is integrable on the x-axis and piecewise continuous on every finite interval, then the Fourier transform exists. So now the question is, let's say you have to find Fourier transform of f of x is equal to e raised to power minus ax. If um, x is greater than 0, if x is greater than 0, then this is the value of the function, and f of x is 0 if x is less than 0. And yeah, our a is greater than 0 here. So let's find Fourier transform. So f of x, that will be f of omega. That will go from minus infinity to infinity, but from minus infinity to 0, function itself is 0. So we just go from 0 to infinity, and we have um, here 1 over root 2 pi also. F of x e raised to power iota omega x dx. Our f0 to infinity, f of x is e raised to power minus ax, and then we have e raised to power iota omega x dx. So if you do this, it's very easy. So finally, you will get 1 over root 2 pi, and this can be written as minus of, here also minus, okay, I think. Minus of a plus iota omega, right, into x and dx. If you integrate this, so you will get 1 over root 2 pi e raised to the power minus of a plus iota omega x divided by a plus iota omega, and then it will go from 0 to infinity. And if you put the limits, you will get finally 1 over root 2 pi a plus iota omega. So this is your Fourier transform under omega. Okay. So you see that you started with some exponential function and now you have converted this into algebraic function. So it's a new function in the new it's a new function in terms of new variable omega, and it's an algebraic function, you can see. So I would also like to discuss about properties of Fourier transform. The first property is that it is linear. Fourier transforms are linear. So if you do it like this, so if you do Fourier transform of f of a of f of x plus b of g of x, a and b are constants. If you multiply two functions with some constants and add them together and take a Fourier transform, that will be equivalent to multiplying taking the Fourier transform of individual functions first and then multiplying with the constants. And this is the property of linearity. Okay. Then you have second property. Let's say you have a function f of x which is going to 0 as your modulus of x going to infinity. Means at your when your x is approaching to minus infinity or your x is approaching to plus infinity, your function is going to 0. Your function has this property and your function is continuous and integrable. Then what we can say, then your Fourier transform of your this function, Fourier transform of derivative of your function will be equal to 1 over root 2 pi minus infinity to infinity, but so it will be equal to derivative of the function and e raised to power minus iota omega x dx, right? This will be your Fourier transform. This will be the Fourier transform of derivative of the function. Now you apply integration by parts. So you take this as the second function and this as the first function. Chain rule of integration. So you have to select first and second function. I have taken this as the second function because we take the function which is easily integrable, and f integration of f prime x will be f of x. So we take that function as a second function whose integration is easy. So 1 over root 2 pi, and we have, just wait a minute, somebody has come at my door. So we have this one, and to apply integration by parts, so firstly, the first function will remain as it is, and we will integrate the second function. So integration of f prime x will be f of x. So we will get e raised to power minus omega x f of x, and the limits will be minus infinity to infinity. And then we'll put a minus here and then integration. Then we do differentiation of the first function. So differentiation of e raised to power minus omega x will be minus iota omega and then e raised to power minus iota omega x, and integration of f prime x again will be f of x and then again dx, and this will go from minus infinity to infinity, right? So let's solve this. So now I told you that this property is going to apply for the function where for which this f of x is going to 0 when x is approaching to minus infinity or plus infinity. So this thing is going to 0 because f of x is 0 at minus infinity and plus infinity. Now we are left with only this thing here. So and this thing, if you remember, if I take minus iota omega outside, so it will be minus minus plus iota omega, and then we are left with e raised to power minus iota omega x f of x minus infinity to infinity dx. This is nothing but Fourier transform of your f of x. So what I can say is, here you have iota omega, and then here you have Fourier transform of your f of x, right? So this is the property. that we are going to use. It means Fourier transform of your derivative of the function is equal to 1 over root 2 pi iota omega Fourier transform of original function. And this is only valid when your original function gives value 0 at when x approaches to infinity and minus infinity, and your f of x is continuous and integrable. This has to be there. Because if your f of x is not continuous, then its derivative will not exist. No? So it has to be continuous and it should be integrable because finally we are integrating this f of x. So then only this will exist. Anyway, for Fourier transform to exist, function should be integrable. Now, so similarly so this is the second property. And then if we just replace f prime x with f double prime x, and all the properties remain same, that your in this case your f prime x should be continuous and your f prime x should go to 0 when your x is approaching to infinity and minus infinity, then you can say that you just replace f prime x with f double prime x. And here also, here you replace f prime x with, here you replace f of x with f prime x. Okay, so then so now your function becomes f prime x, and the derivative of your function will become f double prime x. Then Fourier transform of f double prime x will be 1 over root 2 pi I omega Fourier transform of f prime x, right? And then we already know the Fourier transform of f prime x is this one, so you can then apply this formula. So finally you will get 1 over 2 pi iota square omega square f of x, right? And omega square is minus 1, so finally you're going to get Fourier transform of double derivative of a function is equal to minus omega square Fourier transform of, because iota square is minus 1. So this is your third property. And this will be used, let me give you an example. So let's say you have to find the Fourier transform of x into e raised to power minus x square, and it is given to you that Fourier transform of e raised to the power minus x square is equal to e raised to power 1 by root 2 e raised to power minus omega square by 4. Okay, this is given to you. So Fourier transform of some standard functions will be given to you in the exam, and then maybe you will be asked to calculate Fourier transform of more complex functions. Although finding Fourier transform of this is also not straightforward, but people have solved it, and this is the expression that is given to you already. Now you have to find the Fourier transform of this thing. So now you have to find Fourier transform of x e raised to the power minus x square. So for x e raised to the power x square can be written as Fourier transform of 1 by 2 minus 1 by 2 e raised to the power minus x square to the prime. Because if you differentiate e raised to the power minus x square, you will get e raised to the power minus x square and minus 2x. So this minus and minus will get cancelled, and 2 and 2 will get cancelled, and x will be there. So you will get finally this expression. So do you agree that what I have written is correct? What I have just done is, let me just show it here. I have just written that x e raised to the power minus x square can be written as d by dx of minus 1 by 2 e raised to the power minus x square. Okay, if you do that, you will get the expression. I have done this only here. Now, as per the linear property of Fourier transform, this minus 1 by 2 can come outside, and we will be left with only this, right? And we studied that Fourier transform of the derivative of a function is equal to 1 by root 2 pi iota omega Fourier transform of the function itself. So then we will do it like this, 1 by straight a minute. I think I have done a mistake. If we just see, there is this 1 by root 2 pi, it is missing somewhere. So let me just check it. Check this one.
Step to Bombay.
Yeah, so the mistake is this one. So we just here 1 by root 2 pi will not come because it will be absorbed in this Fourier transform, because Fourier transform is 1 by root 2 pi e raised to power iota omega x f of x, right? So it will be absorbed in this function. So it will not come here. In like this, right? Now, so 1 by root 2 pi will also not come here. Okay, because we are using this relation only here. And now it's fine. Okay. So, okay, so now let's use this relation. So Fourier transform of derivative of a function will be iota omega and then Fourier transform of the function itself. So Fourier transform of e raised to power minus x square, right? Is this fine? So Fourier transform of the derivative is equal to iota omega and the Fourier transform of the function itself. Then we have minus iota omega by 2, and it is given to us that Fourier transform of e raised to power minus x square is this expression. So we'll just insert this function. So we will get minus iota omega 2 root 2 e raised to power minus omega square by 4. Is this fine? So this will be the Fourier transform of x into e raised to power minus x square. And you see that now actually it is not algebraic function, it is exponential function only. So every time we may not get an algebraic function, but it is a complex function. If you see iota is coming here, so it's a complex function. So we may have complex, so we may get complex functions as well for real functions. If we do a Fourier transform of real functions, then we may get a complex function as well. Okay. So we will stop here for today, and maybe you can read about discrete Fourier transform and fast Fourier transform from Kreyszig. It's just after the topic Fourier transform. Okay. So we'll stop here for today, and you can practice more questions from Kreyszig, and you can let me know if you have any doubt. And Fourier transform of some standard functions will be given to you. So Kreyszig has 3 tables. So third table contains a Fourier transform of some standard functions, and using these properties, this property, and the linearity property, you will be asked to calculate Fourier transform of some complex functions also, combining those functions which are given in the table. So then we will stop here for today and we will meet in the next class. Is there any doubt?